Hey friends, welcome to the YouTube channel all about electronics. So in the previous video, we understood the basic steps for designing the finite state machine and we understood the procedure through an example of the sequence detector. And the sequence detector which we have designed was the Mealy type FSM. So similarly, in this video, let us see how to design the Moore type finite state machine for the sequence detector. So the design steps will remain the same. So in case if you haven't watched the previous video, then first please go through that video to clearly understand the design procedure. Alright, so now first let us design a Moore type overlapping sequence detector which detects the 1001 sequence. So as we have seen in the previous video, the first step in the design is to draw the state transition diagram. So in this sequence detector, we will have a one input and the one output. Now as you know, in the Moore machines, the output is the function of only the present states of the memory elements. So here, we will require one more state. So here, this A state is the starting state and it represents the state of the detector when no correct bit in the sequence is received. Likewise, the B state is the state of the machine when the first correct bit in the sequence is received. And likewise, the C and the D states represents the state of the machine when the second and the third bits in the sequence are received correctly. Now in case of the Mealy sequence detector, we have seen that after receiving the 3 correct bits, when the fourth correct bit in the sequence is received, then the output of the detector becomes 1. But in the Moore machine that is not the case, because here the output is not the function of the input. That means here, when the fourth correct bit in the sequence is received, then we need to represent it through a different state. And here, that is being represented through the E state. That means in this E state, the output of the machine will become 1. And in the rest of the states, the output of the machine will remain 0. So using this information, let us draw a state transition diagram of this sequence detector. So here, first let us represent the 5 states of the state diagram. And since it is a state diagram of the Moore machine, so here the output of the machine is represented in the state itself. So like I said earlier, here the output of the machine will become 1 only in the E state when all the bits in the sequence are received correctly. And in the remaining states, the output of the machine will remain 0. So in the beginning, the machine will start from the A state. So now, here since we have only one input, so its value can be either 0 or 1. And therefore in the each state, we can have only 2 outgoing transitions. So in the A state, when the 0 is received as an input, then it will remain in the same state. But on the other hand, when the 1 is received, then it means that it has received the first bit of the sequence correctly. And therefore, it will go to the B state. Now in the B state, when the 0 is received as an input, it means that the machine has received the 2 bits in the sequence correctly and therefore it will go to the C state. But on the other hand, if it receives the 1, then it will remain in the same state. Because in our sequence, the second correct bit in the sequence is 0. But this last received 1 can be a first bit of the new sequence and therefore it will remain in the same state. So similarly, now let us see the 2 possible outgoing transitions in the C state. Now in the C state, when the 1 is received as an input, then the machine will go to the B state. Because for our sequence, after receiving the 1 0, the next correct bit in the sequence is 0. But here, this last received 1 can be a first bit of the new sequence. And therefore, the machine will go to the B state. On the other hand, when the 0 is received as an input, it means that the machine has received the 3 bits in the sequence correctly and therefore it will go to the D state. So similarly in the D state we will have the 2 possibilities. So whenever the 0 is received as an input, then the machine will go to the A state. Because as you know over here, after receiving the 1 0 0, the next correct bit in the sequence is 1. But here, since the machine has received the 0, so it is not part of the sequence and therefore the machine will start searching for the new sequence all over again and therefore it will move to the A state. But on the other hand, when it receives the 1, then it will move to the E state. Because now the machine has received all the 4 bits in the sequence correctly. And therefore, now the output of the detector will also become 1. So as we have discussed in the previous video, in the overlapping sequence detector, the last few bits of the sequence can be a first few bits of the new sequence. And therefore, this last received 1 can be a first bit of the new sequence. So now in this E state, depending on the next received bit, the machine will go to either B state or the C state. So if the new received bit is 0, then the machine will go to the C state. Because when it receives the 0, it means that the detector has received the 2 correct bit in the sequence, and therefore it will go to the C state. On the other hand, when it receives the 1, then it will move to the B state. Because now the 2 bits in the sequence are 1 1. So here this last received 1 can be a first bit of the new sequence, and therefore it will go to the B state. So in this way, we have covered all the possible transitions in the each state. And this is the state transition diagram of the Moore Sequence Detector, which detects the overlapping 1001 sequence. So now, the next step is to draw a state table from the state transition diagram. So in the state table, we will have the present state, the next state, the input and the output. So initially, when the machine is in the A state and when the input is 0, then as per the state diagram, the machine will remain in the same state. But when the input is 1, then it will move to the B state. So here, since it is a Moore machine, so the output of the machine depends on the present state. So in the A state, the output of the machine will remain 0. And therefore over here in the output column, we will write 0. So similarly in the B state, when the input X is equal to 0, then the machine will go to the C state. But when the input is 1, then it will remain in the same state. And once again in the present state or in this B state, the output of the machine is equal to 0. And likewise, from the state diagram, we can write the remaining rows of this state table. So if required, you can pause the video and you can verify the table by yourself. So now, once we have got the state table, then the next step is to check for the redundant states in the state diagram. So for that, in the state table, we need to check are there any identical rows are there or not. So in this case, these two rows seems to identical. Because for the x is equal to 0 and 1, their next states are same. But if you see their outputs, then they are different. That means here, these two rows are not identical. And therefore, here there is a no redundant states in the state diagram. That means here, in this Moore sequence detector, we will have total 5 states. So now, let us do the state assignment. So here, since we have total 5 states, so to represent them, we will require at least 3 bits. So here, we are going to use the following assignment. So here, the state assignment is done in such a way that the state assignment of this B and the E state remains nearby in the K map. Because here, the next states for the B and the E states are identical. So by doing so, the advantage that we get is that in the final circuit, we will have little less logic gates. So of course, you can have your own assignment. And with the different assignment, the final circuit will be slightly different. But in terms of the functionality, it will be the same. So here, we are going to use this assignment. So here, for the 3 bits, we have total 8 possible combinations. So out of which, here we are using only 5 combinations for the state assignment. That means the remaining 3 combinations are the don't care terms. Alright, so now with this state assignment, this is how the state table will look like. So now, the next step is to select the type of the flip-flop. So here, these states are the outputs of the flip-flop. And here, for the 3 bits, we will require the 3 flip-flops. So let's say, the output of the flip-flops are Q2, Q1 and Q0. So here, the same state table is represented in the different way. So here, this Q2, Q1 and Q0 represents the present state of the flip-flop, while this Q2 plus, Q1 plus and the Q0 plus represents the next state. And as you can see over here, this input X is represented in the separate column. So now, let's say for our design, we are going to use the D flip-flops. So now, the next step is to find the required excitations for the D flip-flop. Or in other words, let us draw the excitation table for the flip-flop. So as you know, for the D flip-flop, the output is same as the input. That means here, to get the required next state, the input to the flip-flop should be same as the next state. So in this way, we also got the excitation table for our sequence detector. So now, the next step is to find the Boolean expressions for the inputs of the flip-flop in terms of the present states and the input. Because by applying these inputs to the D flip-flops, we will get our desired next state. So first, let us find the Boolean expression of this D2 input in terms of the present states Q2, Q1 and Q0 and the input X. And using the K map, let us try to find the simplified expression. So as you can see over here, this D2 is equal to 1 only for the one input combination. So first, let us represent it in the K map. That means here, this D2 is equal to 1 when the X and the Q2 is equal to 0 and the Q1 and Q0 is equal to 1, 0. Now if you see over here, then for these 4 variables, that is X, Q2, Q1 and Q0, there are total 16 different combinations. And out of which, here we are using only 10 combinations. So here, the first 5 input combinations represents the min term M0 to M5, while the last 5 input combination represents the min term M8 to M12. That means here, the remaining 6 input combinations are the don't care terms. So in case, if required, then you can pause the video and verify it by yourself. So now, let us also represent these don't care terms in the K map. And now, let us try to find the simplified expression. So here, we can combine this min term M2 with this don't care term. And this group corresponds to x bar dot q1 dot q0 bar. That means here, this D2 is equal to x bar dot q1 dot q0 bar. So similarly, let us find the expression of the D1. So if you notice over here, then this D1 is equal to 1 for the 3 different input combinations. That is min term M1, M3 and the M12. So first, let us represent it in the K map. And like I said earlier, here the 6 input combinations are the don't care terms. So let us also represent them in the K map. So now if you see this K map, then here we can combine this min term M1 and M3 with these 2 don't care terms. And in this way, we can make the group of 4. And likewise, we can combine the M12 with these don't care terms. So here, this group corresponds to x dot q2, while this group corresponds to x bar dot q0. That means this D1 is equal to x bar dot q0 plus x dot q2. So similarly, now let us find the expression of the D0 in terms of the x, q2, q1 and q0. So if you notice over here, then the D0 is equal to 1 for the 5 input combinations. So first, let us represent them in the K map. And like I said, here the 6 input combinations are the don't care terms. So let us also represent them in the K map. And now, let us try to find the simplified expression. So here, by using the 3 don't care terms, we can make the group of 8. And by making this group, we are able to cover all the min terms in the K map. So now, this group corresponds to X. So we can say that this D0 is equal to X. So in this way, we got the Boolean expression for the D0, D1 and D2. So similarly, now let us find the Boolean expression of the output Y. So as you can see over here, this output Y is equal to 1 for the 2 input combinations. So first, let us represent them in the K map. And here, we also have the 6 don't care terms. So here, using these 2 don't care terms, we can make the group of 4. And this group corresponds to q1 dot q0. So we can say that this output Y is equal to q1 dot q0. So in this way, we got the simplified Boolean expression for the D0, D1, D2 and the Y. So now, the next step is to draw a logic circuit from the Boolean expression. And this is the logic circuit for the Moore sequence detector which detects the 1001 overlapping sequence. So if you see this logic circuit, then it is the logic circuit of the Moore machine. Because here, the output is the function of only the present states. So similarly, we can also design the non-overlapping type Moore sequence detector. So here, let me just show you the state diagram for this non-overlapping type detector. And then after, by following the remaining steps, you can easily find the logic circuit. So once again, here we will have a one input and the one output. And here, there will be a total 5 states in the detector. So now, if you see the state diagram, then except the E state, all the transitions will be same as the overlapping detector. But now, since it is a non-overlapping type detector, so after detecting the sequence, it will start searching for the new sequence all over again. That means here, no bits in the current sequence will be the part of the new sequence. That means here, this E state is now a kind of a starting state for the new sequence. And now, depending on the input, the machine will move to either A state or the B state. So in the E state, if the 0 is received as an input, then it means that no bit in the sequence is received correctly. And therefore, the machine will move to the A state. On the other hand, if the 1 is received as an input, then the machine will move to the B state. Because this new received 1 is the first bit of the new sequence, and therefore it will move to the B state. So this is the state transition diagram of the Moore sequence detector, which detects the 1001 non-overlapping sequence. And by following the subsequent steps, we can easily find the logic circuit of this detector. So now, let me show you the simulation results for both overlapping and the non-overlapping sequence detector. So based on the Boolean equations that we got for the overlapping sequence detector, this is the logic circuit of the detector. So here, the flip-flops from the top to bottom are D2, D1 and D0 flip-flops. So as you can see, here the input to the circuit is applied through a shift register. So here, for providing the input to the detector, I have used the parallel in serial out type shift register. That means initially, the 16 bits of data is loaded in the shift register. And then, serially it is taken out at the every clock edge. So this data serves as an input to the detector. So as you can see over here, this output Y of the circuit is equal to Q1 dot Q0. That means the given circuit is a Moore machine. Because here, the output of the circuit only depends on the present states of the flip-flop. So here, in the shift register, the following sequence is loaded. So since the given detector detects the overlapping 1001 sequence, so for the given input, its output should become 1 only for the 3 times. So let us run the simulation and let us check whether our circuit works correctly or not. So first, let me zoom all the waveforms, and first, let me clear all the flip-flops and the shift register. And after that, I am enabling the shift register, and then at the positive clock edge, I am loading the input bit stream in the shift register. So now, if I just run the simulation, then this will be the input sequence. And as you can see, here the output of the detector goes high for the 3 times. That means indeed, this circuit works correctly. So similarly, now let us see the simulation of the non-overlapping type sequence detector. So here, instead of designing the logic circuit, I have drawn the ASM chart of the detector from the state diagram. So this ASM chart is basically a algorithmic state chart of the machine, which is very similar to the flow chart. And similar to the state transition diagram, it shows that how the state transition occurs in the finite state machine. So this ASM chart consists of the state box, the decision box and the conditional output block. So since we are designing the Moore machine, so its ASM chart will not have this conditional output block. Because in this conditional output block, the output of the block depends on the input as well as the present state. That means in the design of the Moore machine using the ASM chart, we will have only state box and the decision box. So as its name suggests, the state box represents the different states of the machine. So here in this non-overlapping type detector, since we have a 5 states, so these 5 states are represented using the 5-state box. So here, the alphabet beside the box represents the name of the state, and the binary value at the top represents its assigned binary value. So in our case, the output becomes 1 in the E state, and that is why over here in this E state, this out is written. So it indicates that in this state, the output of the machine will become 1. So apart from that, this box in the diamond shape is the decision box, and based on the input, it will go to the specific state. So as you can see in the A state, when the input is 1, then it will go to the B state. But when the input is 0, then it will remain in the same state. So if you see this ASM chart, then it is very similar to the state diagram of this detector. So here, just for the comparison, the state diagram of this non-overlapping sequence detector is shown on the right side. So if required, you can pause the video and you can compare them side by side. So now in this lead circuit simulator, which I am using for the design, we have an option to draw the ASM chart of the machine. And after the designing it, you can save it as .fsm file. So once it is saved, then it can be used as an individual FSM block in the another circuit. That means in the another circuit, I can import this created FSM block. And in the new circuit, now this block will perform the specific task as per its ASM chart. So here, if I import this FSM file in another circuit, then this FSM block will work as a non-overlapping sequence detector which detects the 1001 sequence. So now let me also show you that. So here in the new file, I am importing this FSM file which we have designed earlier. So if you see the block, then it consists of the input and output as well as the clock input and the reset input. So now to verify our design, once again, let us apply a 16-bit input bit stream to this block via shift register. And once again, the same sequence is applied to the detector. So here, for the demonstration purpose, I have already connected this circuit. And the same input is also loaded in the shift register. So for this sequence, the output of this non-overlapping type detector should become 1 only for the 2 times. So now, to verify that, let us just run the simulation and let me show you the output. So if I just run the simulation, then as you can see, this is the applied input sequence. And as you can see, here the output of this non-overlapping type detector goes to high only for the 2 times. Moreover, you can also see the states of the machine at the every clock edge. That means indeed this FSM block works as a non-overlapping sequence detector. So in this way, using the ASM chart also, we can design the finite state machine. So if you want to know more about this ASM chart, then let me know in the comment section. And if required, I will cover it in detail in the separate video. But I hope in this video you understood how to design the Moore sequence detector, or in general how we can design the Moore type finite state machine. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.